Okay, the rock and roll is kind of a cool ride. The arms go out like this, and you ride on this ride. Basically, you're hanging by a pivot. So if the ride's not moving, then of course you're going to feel 1g straight down of Earth's gravity, right? But as the ride speeds up, okay, you actually are going to fling yourself out. You're going to be like this. And let's imagine that it doesn't go up and downhill, right? Okay, it flings you out, and it flings you out because basically the g-force you're experiencing is a g straight down from gravity, right? That's 9.8. And then of course the ride is, it's like as if there's a flinging g right there. There's your the centripetal acceleration. And so your frame of reference down is now at like this, right? So this g-force should be the square root of 9.8 squared plus your centripetal acceleration squared, right? That's what it should be. So if you get vertical g's, remember vertical is not straight up and down. Vertical will be just the person holds the accelerometer this way, right? Where positive is up, right? Okay? And so they should be getting this. Now, how do you figure out the centripetal acceleration? Well, the centripetal acceleration should be 4 pi squared r over t squared, right? And we know this radius. We've measured that thing directly. T would be the time at full speed for this one of these cars to go all the way around. So you can do that the same way we did it with the Ferris wheel or the Rockoplane or any of those things. Just click the video all the way around and click once, click twice, right? And look at the time scale, subtract that, right? So that's to me, I can't think of anything else. Now, here's the problem. And of course, the reason why this is fun is that the ride is going up and downhill, right? And so this g-force that you feel is going to get more and less intense because you're accelerating up and down at the same time. So I think what you could do is you could look at that graph. We'll look at that in a second, right? And if you averaged enough of it, if you just did an average of the vertical g-force, then the average should be this, because sometimes you feel lighter as you go over the top of a hill, sometimes heavier as you go through the bottom. But on the average, the g-force should be this, right? So let's just take a look at that and see if we can get that. Let's go to here and go to Oaks Park, right? Go to rock and roll. And there's got to be some vertical data there, right? Here's lateral. We don't want lateral. Let's see. Vertical. Is there a vertical? CMBL. Vertical flipped. Wow. Okay. Lateral. A lot of lateral. Not so much lateral acceleration on this one because remember the thing pivots out. So let's go vertical. Let's see what this one says. Vertical flipped. What does that mean? No idea. Okay. Save link as. Okay. Maybe it's just upside down. Don't save. No, it's interesting. What's an interesting thing? I have no idea what that is. Okay, so let's click on this thing. Let's go options, graph options. Point protectors. Who wants those? I have no idea. Let's just look at the points. I'll bet this is our g-force. I have no idea. Yeah, I don't think maybe we don't have g-force on there. Let's see, is there a lateral? I suppose this is lateral. A reference. CMBL lateral. Let's see what this one is. Save link as. Don't save. Let's see what this does. That truly is lateral. Not much happens lateral because, of course, the thing tips, right? I don't know why that's so unhelpful. Let's make that 10. There you go. And there you go. So it looks like we don't have that data, but maybe you, when you were measuring it, right, maybe you took data with your accelerometer. So you could compare the calculations to the accelerometer or, hey, there's some analysis. Interesting.